Other GLM matrix functions are described in online documentation, and we have already seen GLM perspective in our coding examples. GLM value pointer function takes a matrix or a vector object and returns the address of its internal memory, which in our examples is an array of floating point numbers. GLM matrices and vectors are C++ objects, while OpenGL is a library of C functions, so naturally when we need to pass a pointer to an OpenGL function, using GLM value pointer is a way to do it. Here in our current example, we take our model view and perspective matrices and use value pointer to pass them as parameters in these OpenGL uniform calls, which load our matrices into graphics card, all three of them, and make them available as uniform variables in the vertex shader. The actual uniform data types will be discussed later, but for now I would like to show you another example of printing matrix components using a pointer returned by this function. Alright, so click Build, Clean Solution, then close my current solution and open again my recent project, Lecture 05 Math. And here another example using the address of the internal memory of this perspective matrix. So here we display perspective, and then we can try something like this. So this is a 4x4 matrix. So we call value pointer and pass perspective as a parameter to this call, and this naturally returns the pointer to the first element in the internal array, which is part of the implementation of this 4x4 matrix. So then I set the counter to 4 times 4, which is of course 16, and create this little loop where we just take this pointer, dereference it to print the floating numbers, and increment the pointer 16 times. So the counter will naturally go to 0, and then we get out of our loop. So let's try building this, and before we do, we need to add another include, which is type pointer HPP of GLM library. Now I can build our program and run it, and you can see that we're able to display. First time we display our perspective matrix right here as we would think about it conventionally as a set of rows and columns. But GLM object internally organizes its array of numbers as a set of columns, and in this internal array the first 4 elements are numbers shown here in the first column. Then there's the second column right here. That's the second column. Then the third. And finally the last one, the fourth one. The GLM object that represents this matrix internally organizes its array of numbers as a set of columns, because OpenGL wants us to upload data in the so-called column major order, or what we also call column primary order. And on this slide we have another example of value pointer, also from GLM manual online. All indexing of elements in GLM vectors and matrices is zero-based, which means that the first index is 0. And if you construct a matrix like this identity matrix right here, and if you use index notation, it will give you access to the column vector inside the matrix. So this index 0 provides access to the first column. Index 1 would give us access to the second and third and so forth. So then you can also use C-style multidimensional array or two-dimensional array to access individual components of the column vector. So of course index 0 will give you access to the initial component, initial element in this column vector, and index 3 will give you access to this one. And while this is classic C programming language notation for accessing two-dimensional arrays, in GLM as well as in GLSL, individual vector components are named, and they have names x, y, z, and w. So using x, y, z, and w is equivalent to using these combinations of two indices to specify vector components. We'll have a chance to talk about these named components when we discuss the features of GLSL, the shader programming language in OpenGL. Here we have a scaling matrix example. We construct a vector of 3 elements with some scaling factors, sx, sy, and so forth. And so supposedly maybe it's this vector right here. And then we create an identity matrix, and we use columns 0, 1, and 2 to update values x, y, and z. So 0x will give us access to update this value, 1y will give us access to this one, and 2z provides access to this one. So this is two named components in a vector and also in a column of a matrix. We have already seen examples of translate, rotate, and scale helper functions in GLM. That these helper functions allow you to combine multiple transformations. So perhaps you already constructed a rotation matrix and named it x. Then you can specify it here as a first parameter to translate. And this will mean that first you will be translating and then rotating. Basically, this form of translate call is equivalent to this call where we have the identity matrix to begin with and constructing pure translation matrix and then applying, like I told you in my example, a rotation matrix if x represents it in your code. Similar notes about rotate helper, exactly the same rules apply here, and scale. So this is an example for you to consider. If you're constructing translation matrix from identity matrix, so we start with this identity matrix, and then we want to be able to translate vertices 0.5 units down the y-axis, so this is negative 0.5 on the y-axis, and then we're calling scale, where instead of using an identity, we combine the scaling with the translation, which we have already put together earlier. So this time, both translation and scale will be combined, but the order is important. So in this form, and in this entire example, the scaling will take place first, and then translation will happen next. And this is definitely identical to the rules that we use in traditional matrix multiplication. So if we want to put together this combination of model, view, projection transformations, we need to remember to start with the model, and in order to start with the model transformation, it has to be placed on this right-hand side of our matrix multiplication. Then we want to transform everything into the camera space, so the view happens next, and finally the perspective. And the emphasis here is, of course, on the fact that the order of transformations is very important. For example, it may seem like multiplying transform matrix by scale or scale by transform matrix may yield the same results, but in reality, when you have a cube and it's in its object space, so somewhere around the origin of the system of coordinates, and you want to scale it first, so let's consider this is the first operation and this is the second operation in this scenario. So if you scale it first, you'll probably inflate it in all directions, right? So this cube will become this size. And if the origin of the system coordinate used to be in the center of the cube, it'll stay in the same place, right, in the center of this cube. And then we can move it, right? So we can then move it down, so basically every vertex will be moved by the same amount of size. Okay, so this cube gets moved somewhere here. And in another scenario, where we're doing transformation first and then scaling, the situation goes like this. So we have our original cube, once again, possibly with the center of the system of coordinates, right in the center of our cube. And now we're transforming it. So when we're transforming it, it ends up being shifted by the same amount down, like this. So it ends up being here. But when it gets scaled, then it will be inflated still relative to the origin of the system of coordinates. So it'll end up going somewhere like this. Okay, so it will end up somewhere down here because it will be expanding in sort of like these directions, as opposed to the original scale first, transform next was expanding from the center or origin of our system of coordinates in all directions. So you can see that it's guaranteed that reversing these operations will end up placing our cube in different places in our world. So clearly these things are not the same.